In this video, we're going to implement a backpropagation scheme neural net for a network with an arbitrary topology. So in other words, we're not going to have explicit layers. So the connectivity structure is going to be given entirely by a two-dimensional matrix here. And so we'll make the size, so we'll have like 3 inputs, and then we'll have like 5 hidden units, and then 3 outputs. Just so with no explicit layers. Maybe I'll make that even bigger. So, I mean, I guess the input and the output layers are explicit, but that's it. You know what? I'm gonna make this. So the first thing we need to do is randomly initialize the network itself. So we're gonna loop over the network, and I think we're also gonna have biases. Actually, well, I'll be explicit. So these are the weights, like. Okay, so this is the connectivity matrix, and so there's like a 0 if the 2 units are not connected. Otherwise there's a weight value. So also for every unit we're going to need the weighted sum computation. And then the just the output, or the nonlinearity, which is the output. I guess we'll just call it NL for nonlinearity. So, yes, this will be a forward pass. So, pass. We will fix the outputs for the input units. So this is the nonlinearity, aka the output. And we said it'll be 3-dimensional, so there you go. And then we just loop over the remaining units. So starting at 3. And for each of those, we're going to have a sum. And we're going to loop over the units that it reads from. So we're going to start at I, go to U, and then we're just going to say sum plus equals the output from J times, actually we can make this just equal to the bias for I. So the nonlinearity from J times the weight connecting I to J. So that's the sum, and then we say the nonlinearity, or the output from unit I, is just equal to whatever the nonlinearity for the sum will be. Typically you use like a sigmoid. I think I'm just going to use a square function because who cares? And so that's the forward pass. Right, so the interpretation of the weight matrix is, it says the connection, so like unit, say 5, can only read from units 0 through, so this should actually be 0 through I. Oops, yeah. So unit 5, for instance, can only read from units 0 through 4. So to compute the output, or to compute the weighted sum, actually we do need to store the weighted sum as well. So to compute the weighted sum, we loop over all of the units that the ith unit reads from, and then we multiply by the weight. So yeah, that is the entire forward pass. So I think what we'll do is we're going to animate the operation of the network on random inputs. Yeah, so we'll pick a random input value. So we'll say input equals, down here you say, you take the input, you shift it 0, and then you end it with 1, and then basically the same thing, 1, 2. Okay, and then we're just going to draw. We're going to do a forward pass, and then we're going to draw the activations. So we're just going to visualize the activations. So we're going to draw a rectangle at, so I don't know, we'll do 50 pixels. I times 50, 0, 50, 50. And the fill color will be, again, we're gonna linearly interpolate between I think just red and green. So oops, 225, 0, 225, 0, and the lerp is going to be the nonlinearity, or the output, for unit I. Yeah, I think I might do a sigmoid, that way. So see, the sigmoid is 1 over, like, 1 plus math exponent negative sum, maybe. So now we know we're between 0 and 1, which is better for everybody. Okay, so there we go. So these 3 units are the input units, and you know, these 3 units are the output, and then we have our hidden layers. So that's a so here's a quick idea. Let's say I want the 3 output layers to be all 1, independently of the input. So we're going to learn a constant function. So we're going to use backpropagation to do that. So we'll just have a backpass. So this is where we'll implement backpropagation. And I think we're just saying, like, the L2 distance. Yeah, I think you have to do math dot square root, and then the output at 11 minus 1 squared. Plus same thing for 12 plus same thing for 13. So that's like our total error. And we have to now convert to a float. Now we go backwards. So we're going to have an array for the effect on the error for the output, right? Because every unit is doing 2 computations, right? So we're going to say like the effect on the error from the weighted sum for a unit and then the effect on the error from the output of the unit. So if our unit is the output, so what we're saying is an L for 13 is going to be, so we're saying if I change the output of the very last unit, how does that affect E, my total error? And so it's a partial derivative computation. So like, I think in general, DDE is going to be, so we have the square root, so it's going to be, let's say like, it's going to be 1/2 times then to the -1/2 power something times the inside here, and then that times the, it would be 2 times the whatever the unit is minus 1, and then times 1. So I think we're going to split up the, so the like the sum for the error is this part, which we need to treat separately. And then this is the, see, and then we can write it directly. So the effect on the total error of the output of the 13th unit is going to be 0.5 times SE to the, well, 1 over math dot square root SE times 2, so that goes away, times the output for 13 minus 1. So that's my computation. I don't know if that's right, but so we can do that for all of the output units. So 12 and 11, and 12 and 11. And then we need the same thing, we need to backpropagate one step within the unit. So we need to handle the weighted sum. So, you know, it's going to be the effect of the output, which we just computed, times the effect of the weighted sum on the output, which, since we're using the sigmoid, that will be alright. So yeah, so these are the output units, and so we have the effect on the error of say the weighted sum for unit 11, which is one of the output units, is equivalent to the effect on the error of the output of that unit times the effect of the weighted sum on the output of that unit, which is just the derivative of the sigmoid with respect to its input, and the derivative of the sigmoid has this form. So that gives us the effect on the total error for the output and the weighted sum for each of the output units. And now we can just backpropagate to all of the remaining units. So in general, the effect, now this is going to be a sum actually. So we're going to have to sum over, well, I mean, like in general, the effect on the error of the output of unit I is going to be the sum over all the reads, all the units that read from unit I, times their effects on the error, times the effect of the output of NL I on the weighted sum, which is going to be the weight. So we're going to have, so to get all the reads, all the units that read from unit I, we're going to start I plus 1, j is less than u, j plus plus, and so we're going to have to take a sum here. So we're going to be summing. So j is a unit that reads from unit I, and we've already computed by assumption the effect of the weighted sum for j on the error. And so then we just ask, what is the effect on the weighted sum value for the output for unit I? And that's just going to be the weight that connects j to I. So in other words, j reads from I. And then and I believe that gives you the entire value for E, the output. It just equals the sum, and then E for the weighted sum is ENL I times NL I times 1 minus NL I. This value is the effect of the weighted sum for I on the output of I, and it's it is the derivative of the sigmoid function. So that may or may not work. So that's your backwards pass, and then I think we're going to compute. So then we then want to compute the deltas for all the weights and all the biases. So we're going to have the delta matrix for the weights. And so the delta for the weights is yes, we're gonna crank on through all the weights, and this time the order doesn't matter as much. So we crank on through the weights there, and then we're gonna say the D for the weights is just the effect on the total error of this weight. So like if we increment this weight a little bit, now this weight is saying that I reads from J. So if we increment this weight a little bit, what we're doing to the error is going to be the effect on the error for the weighted sum for I times the activation from J. And then for the bias, if you increment the bias, it's just whatever the effect of the weighted sum for I is. And so then that gives you your weights, your D weights, and your D biases. And that should actually be in the back pass. I put that in the wrong. Yeah, I just put that in the wrong unit. That's fine. Alright, so now we're updating everything. We're going to have a learning rate. And so then we're just going to... Yeah, we are going to have a separate training step. So in a train step, we have a random input. And then we run a forward pass. Then we run a back pass. Now the back pass, the desired output is hardwired to the code. But then we're just going to update the weight matrices. For now. Typically in a train step you do like a batch, so you'd run over multiple inputs, but we're going to ignore that for right now. So we're just going to say biases minus equals learning rate times the delta for the bias for I, and then the weights for ij minus equals the learning rate times the delta for the weights for ij. And so we might, let's see, so I think we'll run a training step, and then we'll visualize what's happening. So it should be that the output units slowly become the constant function. So these guys should slowly start to only output, I think, green. They should become more green over time, which kind of appears to be the case. So, yeah, is that right? I mean, it's kind of hard to tell, but yeah, it looks like we've successfully found a, we've successfully learned a constant function. I think another thing I'll do is I'll visualize the weights real quick, since we're actually updating them now. So, if I can find a thing here. So we're going to visualize the weights themselves. I think we'll just use this. So we'll visualize the biases for I, and then we'll put that at like 700, no, just put that down 700 pixels, and then the weights be the same thing, except it'll just be weights j, although I think the weights can be arbitrary, so we're gonna have to map. So we'll map the weight value from, say, -1, to 0, 1. And then put a rectangle at I times 50 plus j times 50. I think that's right. Alright. Ran out of the biases got cut off. So I'm gonna put the biases, well, no, just make this bigger. So make that like, just make that 1,000. And for the training step, we'll do it a couple times. For some reason, it ain't showing my biases. And that needs to be like 900. There they are. You also need to map from like -1 to 1 to 0 to 1. Okay. Alright, so you can see like it's learning the constant function. Also, just to make sure it's working, let's have it try to learn the constantly false. So now it should now output all reds instead of all zeros. all reds instead of all greens. Yeah, so it's learning to output all the reds. Now the not seeing like the weights changing much. Yeah, okay, you can kind of see some weights getting updated. A couple of the biases, I guess.